The product and quotient rule. The learning target, which you should write down at the top of your notes. Again, make sure that you're dating and labeling your notes because these will be submitted. The learning target is I can find the derivative of functions that have the format f of x times g of x and f of x all over g of x. Before we actually delve into what is the product and quotient rule and how it relates to derivatives, let's have a little bit of background. So questions to know for the quiz at the end. Number 1, why is taking an integral useful in math? 2, why is a derivative useful in math? 3, when do you use this quotient rule? 4, when do you use the product rule? And 5, you're going to be expected to find the derivative of f of x equals 2x squared minus 1 all times f of x plus 3. All right, before we dig into our learning target, I want you to go ahead and sketch this table in your notes. One titled as the integral, and make sure you put the little symbol for the integral here, followed by dx. Usually there's a function that goes right after the integral symbol. And then you want to title on the other side derivative and f prime of x, where this prime notation is like an apostrophe. So I'm going to go ahead and start talking about this derivative side first, and then we'll work into the integral. So what is a derivative? So what is it? It is the slope of the tangent line. We also call it the derivative. It can also have this dy dx notation instead of the prime notation up here. Here's the basic rule. This right here, the basic rule, is called the power rule. If you have a function x to the nth power, then the derivative of the function is you bring the power down and subtract the exponent by 1. So that's the basic rule that we've been working with. But why is it useful? So finding the slope of the tangent line can tell us the instantaneous rate of change of an object. So instantaneous rate of an object. For example, a traveling car's instant speed at 5 seconds. So what do I mean by that? So if we, and please make sure you sketch this down, if we have this graph, and let's just say this graph represents, I don't know, a car traveling, it's just decreasing and then increasing in speed, and for the moment we can ignore negative time intervals. But this red line right here, this red line is called a secant line, and it gives us the average rate of change of the car. But once the secant line, once this like Q point right here gets closer and closer to this P point, we have this green line, which is called the tangent line. Notice that the tangent line intersects the point P at exactly 1 point. This slope of this green tangent line will tell us the instantaneous rate of, for example, a car at, let's say for here, 2 seconds or something. So that is what the derivative tells us as far as real-world context. Now, the integral. What is it? It's an operation that takes the antiderivative. We also call it an accumulation function that accumulates a quantity, specifically a quantity under a graph's curve, basically like the area under the graph's curve. The basic rule for this one is if you have f of x equals x to the n, then the integral of x to the n is going to be, and here's the rule, 1 over n plus 1, x to the n plus 1. This is also the antiderivative. It's like going backwards from the derivative. Let me just circle those formulas. Well, let me circle this formula, and then we'll circle this once we talk a little bit more about why it's useful. So then why is knowing what the area under the curve useful in math? Well, finding the area under the curve helps us determine the quantities under something like a rate graph. Like for example, if you have a profit function. Let me bring up this type of problem. Let's go ahead and read it. So area under the curve does offer a convenient way to think about integrals. Integrals can be used in a variety of contexts. That's why we call it an accumulation function. It accumulates a quantity. So for this one right here, we have this integral from 0 to 75 of P of C dc is equal to 125.93. P represents the rate that a coffee shop makes in profit in dollars per ounces of coffee sold C. So basically, if I want to find the area of this profit rate function, see the rate that the coffee shop makes profit per ounces, If I want to find what does the area under this curve represent, well, what I could do is draw like a basic rectangle, right? I know if I want to find the area of a rectangle, I do base times height. Now for this problem, the height is going to be my rate function, P of C, the profit, P. So I'm going to go ahead and label that P of C, and remember it was dollars per means division, ounces. That's my height. And my x-axis would be down here, and that would be coffee sold, C. Like that, see? My height, or my y, is dollars per ounces, and my x-axis is ounces. Now to find the area of a rectangle, all you do is base times height. So if I do base times height, or height times base, either one, what we notice is the ounces will cancel out and give us the total that's accumulated, which in this scenario is dollars. Sometimes when you find the area, for example, under a velocity curve, and velocity is a rate, it'll give you total distance traveled. But in this context and in this situation, the variety, right, it'll give us dollars. So that's why taking an integral is useful. That's what it's used for. And then again, the basic formula for taking the integral is this right here, 1 over n plus 1, x to the n plus 1. So again, please make sure you get these diagrams in your notes. You want to know what the difference between the two and when they're used. This is a funny diagram of what we're talking about, because there's, differentiation, that's taking derivative, and then there's integration. Look at this, right? There's like you try to do something called integration by parts, which we will be learning. Or you could try substitution. Are you done? Nope. Question mark. Oh, there's a bunch of other formulas you could try, right? So that's for integration. But for our notes today, right, we'll get to these later. For our notes today, we're going to be actually still going back to derivatives, basically the slope of the tangent line. We talked about power rule, but in these notes, we're going to go ahead and talk about what is the product rule, how do you use it when you take the derivative, and what is the quotient rule, when do you use it, and how do you take it, how do you use it, how do you take the formula. And then there's of course something called chain rule, which will be for another video. And then it's pretty straightforward from there. But like I said, we will talk about integration later on. Again, if you want to check out this comic, I got it from this website. Those are going to be our focus points. Okay, so we have worked with taking derivatives of functions that have the basic format f of x equals x to the nth using the power rule. Now we're going to take derivatives of functions that have the format h of x times g of x. That means two functions multiplied together. There is a specific rule for when you're multiplying functions together and taking the derivative. Again, these are when two functions are multiplied together. And again, we're also going to take the derivative of functions that have the format f of x over g of x. That's when two functions are divided. Again, please pause this video to get the notes down. Okay, so let's go ahead and talk about how do you use the product rule. So remember, product means multiplication. If you have two functions, and I went ahead and color coded this, h of x times g of x, then the derivative, h prime of x, is going to be h prime of x times regular g of x plus regular h of x times g of x. It's a funny long formula, but I like to say it like this. Take the derivative of the first, keep the second the same, plus leave the first alone and then take the derivative of the second. I like to kind of say it like this, and it kind of sticks, right? Once you get enough practice. So if you have two functions that you're multiplying, how you take the derivative is the derivative of the first function times the second function, plus the first function times the derivative of the second. We're going to see an example of this in a sec. Now, what is the quotient rule? How do you use it? Whenever you have two functions that are being divided, that's when you know to use the quotient rule. It looks longer, but it's very similar to the product rule. If you got the product rule down, then this one might come a little easier. So the derivative of a function that has a format like this is going to be take the derivative of the top function while keeping the bottom the same, minus leave the top function alone, take the derivative of the bottom function all over bottom function squared. And that's right here, the part I just said. And like I mentioned, it looks long, but once we put these into practice, it should be okay. Again, please make sure you get this down. All right, let's get to some practice. Now this example right here, this looks very similar to the quiz question that you're going to be asked to do, which is finding the derivative of one that looks just like this, except a few numbers are switched. So step one is to notice that it's this function times this function. So that tells me already that I'm going to be using the product rule because I see multiplication happening. So I have this times this. So this right here is just the rule on top. It's just a reminder of the rule. And I went ahead and color coded green for my first function, red for my second. What I'm going to do in my next step is I'm going to go ahead and take the derivative of the first function while keeping the second the same. Then I'll keep the green function the same and take the derivative of the red. The derivative of this right here, bring down the 2, that's going to be 10x. Keep this the same. See, 10x. And I kept it the same. Then you leave the first function alone, don't do nothing to it, and then you take the derivative of the second function, and in this case, the second function, the derivative of 4x plus 3 is just 4. For this one, if you would bring down the 1, it will be 4 times x to the 0, and x to the 0 is 1. So that's why you just get 4. And then as a reminder, the derivative of a constant is 0. And that's why this one, the derivative of the constant was also 0. Okay, once we have this set up, we're going to go ahead and just do some arithmetic. Combine like terms, and then we'll be done. So 10x is going to go ahead and distribute. This 4 is also going to go ahead and distribute. Then we're going to go ahead and combine like terms. So 40 plus 20 is going to be 60x squared plus 30x minus 4. And I think I've done all I can. I've found the derivative, everybody. Now let's go ahead and do another example with the product rule. With the product rule right here. But this time we have the square root of x times 2x minus 3. So this is my product rule, and again you identify like, oh, I'm using product because this is square root of x times 2x minus 3. So we will be using product rule. The only issue though I have is this square root of x right here. We have to remember that the square root of x is the same thing as saying x to the 1/2 power. Remember to keep that in mind. So that's why my first step is I just rewrote everything, except I made sure I changed that square root to x to the 1/2. All right, let's go ahead and do our derivative rule. We got to take the derivative of the first function while keeping the second the same. Then we're going to add, leave the first function alone, and then take the derivative of the second. All right, it looks like I applied the rule. Notice how I brought down 1/2, subtract 1/2 by 1. That's how I got negative 1/2. I kept the second function the same. Then plus, keep the first function the same. Taking the derivative of this red, or second function right here, is just 2. After this, we'll go ahead and combine like terms. Well, after we kind of distribute, right? So 1/2 x to the negative 1/2 times 2x is just going to be x to the 1/2, because 1/2 times 2 is just 1, and then we have negative 1/2 plus 1 is positive 1/2, so that's how I got this first one. Then we have negative 3 times 1/2 is going to be negative 3 over 2, and then it's going to bring with it the x to the negative 1/2. So that's for the first components. Then this one right here is just 2 times x to the 1/2, that's 2x to the 1/2. Now that we hit this point, we could go ahead and combine like terms. This one is the same like term as this one. So we have an imaginary 1 plus 2. And I've combined all the like terms that I could. I'm finished up until this point. Okay, so that is our product rule. That's the end of our product rule examples. Now for the following video, we will be talking about how to do a problem like this. So, but we're going to go ahead and save that for a different video. Please make sure that you try to get some practice on the product rule. I'll try to put some additional ones, like taking a look at Khan Academy and things like that. But stay tuned for our next lesson, which is going to be part 2, which is how to do the quotient rule. That's when you have division of a function. And again, this is right now we're doing a derivative rules. We'll pause on our integrals for the moment.